Hello, welcome. So we'll be using this particular link to do our classes. Now, I've put a waiting room so that really no one can start the meeting except me. But I think I'm going to change that and make it possible for you people to join in before me. But because now you see I have to do so as some extra work. But please, as I said last time, don't just join anyhow, join, close to the time of our classes, because when you join in, I get messages in my email, and it has been disturbing me with some other links that I've created. So let's do that. Please let me know if you can hear me so that we can start.
Yes, we can.
Okay, thank you. I'm at the university, so I'm using Makere internet. But if anything happens and my network becomes bad, do let me know, and I can use my phone. Now, last time we were doing satellites. Unfortunately, I've not shared the notes. I'm going to share the notes. By the way, Ella, I've shared the link with you where I put the videos. So please, you can share the link with the students so that everyone can go there and download a copy of the videos. I'll be posting them hopefully as soon as we finish the lecture. Usually there is a bit of a processing time, but once it becomes available, I'll be sharing them. Please note that sometimes they can be large. This particular one is about 330 megabytes, so that's not too big, but I've seen some big ones. Anyway, so let's start our lecture. For whatever reason, please just ask me, put your hand up and ask. So we were looking at this, and now, actually, before I do this, I'll be sharing with you notes, like fresh notes. I'll not be sharing notes where I've been writing. But if you want to see what I've been writing, obviously you can watch the videos because those are recorded. But I'll be sharing a clean copy of the notes. So anyway, if we start our meeting, we talked about low Earth orbit satellites, which are about 500 to 1,500 kilometers above Earth. We talked about medium Earth orbit, which range from around 10K, 10,000, which is that, to 20,000 kilometers. And then the low Earth, the geostationary orbit, which is at 5,000, something like that, 863. I think that's the one. I've seen 35,870, so usually if you're given a distance, it's the one you use, but we know that it is a certain distance above the Earth, and it is geostationary in the sense that much as it is moving around the Earth, it is basically moving at a similar speed to Earth, which means that to the viewer on the surface of the Earth, you see the satellite suspended in exactly the same spot at all times, as long as your reference point does not change. That means that it's like two cars moving side by side on the road. It's as if you're looking at the other car, it's as if it's stationary. It's just because you're moving at the same speed. Now, coverage increases with altitude. It goes without saying. If you go higher above the Earth, you see bigger space. The period will also increase with the altitude. The period is how long it takes for a satellite to move around the Earth. Satellites closer to the Earth, first of all, have a shorter distance to the Earth, but they may also need to move at a faster rate to counteract the forces like gravitational force. So they tend to move faster, but also their orbit is obviously shorter if you look at the circumference, because they are lower in altitude. And then finally, the delay increases with altitude. So the delay really is, if I send out a signal to the satellite, how long does it take for me to get a response? And even if you remove the processing time, it is still going to be longer, that propagation time. So usually with this delay, we have two types of delays that we add together to create the total delay. The first one is the processing time. So if I send out a signal, the satellite receives it, processes it, and sends it back. That usually takes a little bit of time, a few certainly milliseconds. And we know that what is doing most of that is the transponder. Then, but there's a time delay it takes to move from your Earth station to the satellite, and from the satellite back to the Earth station. That is called propagation time. It is, you can call it a round trip time, right? Round trip time. You can call it a two-way propagation delay. Whatever, you know, description you use, it just has to make sense. Now we know that for the geostationary orbit, if it is at 35,863 kilometers, the total distance, so basically these delays are propagation delay, and processing delay. This happens at the Earth station. Okay, now it means that round trip is equal to 2 times 35,863. That is in kilometers. If I want to find the time it takes for this, the propagation time, the so-called delay for the geostationary orbit, I can do this. We know that time is distance over speed, which is 2 times 35,863. Kilometers is obviously 1,000. Over the speed of the signal is the speed of light, which is 3 times 10 to the power 8. Now, the denominator, the numerator is in meters in this case, and this is in speed is meters per second, so that our time will be in seconds. Can somebody give me the answer for that calculation? Has anyone done the math? Sorry, can you guys hear me? I hope that some of you are doing
Yes,
this.
we are calculating.
Really? I told okay, please carry on as I tell a joke. I told you, can you calculate? I waited, then I pulled out my phone and did the calculation, and I have the answer. So why is it taking you too long? Okay, I see something in the text, 0.239. Yes, that's right. So we can say 0.239 or 0.24 of a second. So if I send out a signal to the satellite and I receive it back, if we assume that there is no processing delay at the satellite, it's an assumption because we actually know in reality it's there, then it will take 0.24 seconds for me to get back that signal. That is a quarter of a second. Now, usually there is some processing delay, so we push that to about 0.25 of a second. Okay, let's see. Yeah, thank you, Victor. Now, this processing delay, if I'm here, you know, when we speak, if you're speaking to somebody that is far away, like in Europe or the US, there's usually a delay. I think also if you probably speak on WhatsApp, there might be a delay. I don't usually use WhatsApp for voice. And usually that delay comes from the propagation. Now, it is very apparent to a human being if there is a delay, sometimes you end up actually speaking at the same time because you wonder if the other person has heard. If you're speaking on the satellite, it is possible that most often you hear that delay, you sense it. The brain may not sense a delay of about a millisecond or less, but when it becomes just a big fraction of a second, like a second, or if somebody listens to you and then delays for a second, it is very perceptible. And this can be a disadvantage for satellite, particularly for voice. That as you speak, there is that delay that you have to wait. I think you've also seen it on these big television stations like CNN or BBC. If a reporter is asked a question, the TV person would usually first stop talking, and the other person is actually still listening, because of the transmission delay. And we know that with these TVs, especially things like CNN, BBC, the signal that you see relayed in Africa usually is through satellite. So there is that delay when you're dealing with satellite because of the enormous distances that are involved. But if you're dealing with data, then it is fine. Imagine if you're opening an email and it opens in a quarter of a second. I mean, you don't even notice that. In fact, you don't expect it to be that fast. Okay. If you have a question, please do ask. Let's continue. Yes, I think we would have, we didn't go through this. So I said that actually this is a picture that shows the Earth, the size of the Earth and the size of the geostationary orbit to scale. So that is actually how far these satellites are from the surface of the Earth. Really long, like what, 4 times the diameter of the Earth? Probably. That means if this is the diameter of the Earth, okay, then you need maybe that and that. Okay, so about 3 times d. That is about 3 times the diameter of the Earth if you go through the Earth's core. Now, the satellite pictures here that you see on this are actually not, they are actually not to scale because the satellites wouldn't be so big in that context. Now, this is, I think you may see something like this. I think I should say, I think you have seen that small modification that I've made. So it is degrees, it was like 1,200. So if you have 3 geostationary satellites, 120 degrees apart, you actually cover most of the Earth. So imagine you have, okay. Imagine you had a satellite here and a satellite here and a satellite here. Here is hoping that those are, so this satellite will cover part of this. That satellite will cover part of that, and that satellite will usually cover like that. So in fact, the whole Earth is covered. It's just that the challenge comes from the orbital plane of these satellites, the fact that they are in the equatorial plane. In fact, they are moving around the equator. That means they cannot cover the poles of the Earth, because obviously the poles, the Earth is a sphere, so it can't quite reach the pole region or the polar regions, sorry, because of that curvature of the Earth. But if it were possible that if it was the Earth was flat, for instance, then you could cover it with just one geostationary orbit or geostationary satellite, as long as it's in the geo orbit. Obviously, if you reduce the height or the altitude of the satellites, then you don't have that kind of huge footprint to cover the whole Earth, a third of the whole Earth. So each geostationary satellite can cover about 25 to 26, 27% of the Earth. So if you separate them nicely so that they don't overlap too much, then you can cover the whole Earth, or at least 75% of the Earth, using using geostationary, 3 geostationary orbits. Now we know that the polar regions are generally not habitable places. Of course, people go there for research and stuff, but it's just nice that most of the population in the world is actually either side of the equator, but they don't actually go that deeper towards the polar regions. So that coverage, so sometimes they say 3 geostationary satellites cover the whole Earth. Really what they mean is the habitable Earth is essentially all covered. But if you look at the whole surface area of the Earth, then the truth is that it's about 75 to about 80% coverage. The advantages of the geo, obviously, are very clear. One, no problem with frequency changes. I'm going to explain what this means. I can add here no Doppler shifts. Okay. No Doppler shifts. Doppler is a name, Doppler shift. I'll explain this in a moment. The other one is tracking of the satellite is simplified. Usually satellite tracking means you need to know where the satellite is. So usually when you switch on your GPS, the GPS will take a bit of time to resolve the location. During that time, it is tracking the satellites to know where they are, and they receive the signal and try to resolve their location and so on. The other thing is that you may be tracking your satellite for any other reason. So you want to know where exactly it is because we've said that these things are moving. Now, because the geostationary orbit is designed in such a way that there is no relative movement between the Earth and the satellite, meaning that the satellite is always in the same location above the Earth, there's no need for tracking it because, it's always there. So I just point there my antenna, and for all eternity, my antenna will always be pointed at the satellite. Now, if you have had DSTV at your home or you've seen how they deploy DSTV, for instance, when they bring the dish, the guys do some bit of antenna location or antenna azimuth optimization. Really, they are trying to track, to know where the satellite is. They don't really have the tools, but they just look at the signal. If they get a good signal, they say, okay, this is the perfect position. But that may not work for a situation where you need very good quality and maybe both your terminals are moving. Because if the satellite is moving and perhaps even the handset or the receiver is moving, then you need clearly to be able to track. Then third is, of course, it has a huge coverage area. That is an advantage, of course. The disadvantage is, after the signal has moved 35,863 kilometers, I don't care how much power you have transmitted, the signal will usually reach when it is quite weak. Now, if we look at the downlink, and we said that the downlink is the link from the satellite to the dish, to your Earth station. This is the downlink. Usually, if you're going on the uplink, your Earth station is a huge undertaking. It's a huge installation, and you can put a lot of power and pump it towards the satellite. But the satellite is a small thing which runs on battery and solar power. There is no way of generating a lot of power to transmit towards Earth. So most of the time, the power that the satellite repeater actually transmits is limited power. So after going through that whole distance, it will reach when it is quite small. The polar regions are poorly served. I feel like this point, maybe say by geostationary orbit, because when you look at medium Earth orbit and low Earth orbit, they cover the polar regions quite well. So there's that caveat there that this actually really means the geo orbit. People are still coming in. I believe that they didn't know where we were. And then the other thing is that there is substantial signal sending delay. This is a problem if you really need quick responses. So for instance, if we are doing data, as I said, even if we're using the geostationary orbit, there's not a big deal because 0.24 of a second, even if we made it a second with the data, we wouldn't really be bothered. But there are some situations that require faster responses. So imagine that I have self-driving cars and they have to communicate using satellite, so that if this car and there is another car coming and they are about to collide, this has to first send a signal to the satellite, and that one has to tell it what speed, then that one has to go back to the satellite and come down here before they make a decision to reduce speed. Do you know how self-driving cars work? But even if you don't know, you might get that sort of concept. So it means that if there's going to be a lot of time delay before taking action, it is possible that a crash or a collision might happen. If you're doing things like precision surgery, you're not going to use satellite. But if you're doing things like precision surgery and you have to communicate, or you're doing self-driving cars, these are things that require low latency. Latency is the delay. So if I say delay, it is the same as latency. So they need very low latency, and so you need a different communication system. Mobile can work, but even more things like Bluetooth, like Zigbee, some type of communication system that works well over a shorter distance would work better in that case. Any questions? Okay. If there are no questions, let's continue.
I have a question.
Okay, please.
Like the speed of the electrolytes that move.
I can't hear.
If you mention the speed at which the satellite move, that
Derek, I can't hear you. I don't know if it's your network.
Hello, can you hear me?
Yeah. Yes, please.
I was relating to what you had talked about the speed at which the satellites move respect to their distance from the Earth. At some moment, it's more like you say the ones on next near Earth move at a faster speed than the ones far away.
Yeah.
Syncing with me so well, because I felt like satellite is to be geostationary, and it is very far away from Earth to move at a faster speed to keep up with Earth, to be geostationary compared to one that is to Earth. I don't know, probably, but you mentioned there were kind of two kinds of speed, so I didn't get the entire point.
I think I get your question, and I can understand why perhaps it is a bit confusing. I'll do my best to try and clear it. So I've been actually saying that geostationary orbit, so let's imagine that that is the orbit. This is my Earth, and that is orbit. I've been saying that geostationary orbit satellites move at the same speed as the Earth. Like they because we know the Earth rotates once a day, and the geostationary orbit also does it once a day. So it's like the same day for the geosatellite. I said that, but what I really meant was not, it was more of relative speed. So that at all times they are in touch, there is no relative speed between them. So maybe the geostationary orbit has to move at a faster rate, but the line between this point and that point, especially if this is where our geosatellite is, that line always stays, the line between those 2 points always stays the same, it doesn't change. That's what I mean. So maybe the satellite in the geo orbit moves faster, but there is no relative speed between the Earth and the geo. Now, I know that wasn't the entire question that you said. Now, if we look at something like low Earth orbit, the low Earth orbit satellite moves faster than the geostationary satellite orbit, mainly because it has got to overcome more gravitational pull. I told you that when you launch something into space, you have to give it a speed, but you have to give it a speed so that it can counteract the forces that are acting upon it, so that it can stay within that orbit. Now, the low Earth, now if the low Earth orbit satellite behaved that like a geostationary orbit, so that it is also, if I draw a line from that point to that point, that it will always be there at all times, that means that there is no relative speed between the low Earth orbit satellite and the Earth, then obviously the low Earth orbit satellite would have to be moving at a much lower rate. However, remember that actually if you're looking up and you see a geostationary a low Earth orbit satellite come up from the horizon, it will be only 20 minutes before it goes over the other horizon. So on the one hand, its orbit is shorter. Okay, the circumference of its orbit is a shorter distance compared to the geo. But the reason why it has actually to move faster in the end is that it has also to counteract the forces that are pulling it, the gravitational forces, for instance, that are pulling it back to Earth. So you give it a much faster speed. Of course, you could read a bit more about it, but generally that is the context. The two would be, the low Earth orbit satellite would move at a slower pace compared to the geo if it was also having no relative speed between itself and the Earth. But this is not the case. Okay. But you could read a bit more about it. Yeah, okay, pleasure. All right, so let us look at low Earth orbit. These are in my opinion, the ones that can actually revolutionize our world. Not to say that the other ones, but these are a bit much closer to us. Distances of 500 kilometers or 1,000 kilometers, 1,500 kilometers. We've also seen that somebody gave us a reference here that the low Earth orbit also is the same area where we have the International Space Station, which is at about 250 kilometers above the Earth. So when you're launching into this, you're launching satellites into this orbit, it is much simpler, cheaper, easier, and so we can also give localized services, so that if I only want my TV in Uganda, I don't need to have the whole signal everywhere in the world, and so on and so forth. Now, these are circular, or they can be slightly elliptical orbits with a radius of 500 to 1,500. It could be all the way from 200, the edge of space, which is about 110 or 100 kilometers above the Earth, all the way to about 2,000. So all that orbit can be called low Earth orbit. The coverage diameter is about 8,000 kilometers because of the fact that it is closer to the Earth, so it doesn't cover a very large area. It has a round trip time or delay of less than 20 milliseconds. Remember that for the geostationary satellite, we found that the delay is about 0.24 of a second, which is, I think, 250 milliseconds. This one, the delay is 20 milliseconds. So if you're speaking on phone, you can't feel like the other person is delaying to reply to you. That apparent delay is no longer noticeable by the brain. And so that is good. If you're using that for voice, it is also much better. Even the devices, the reception devices on Earth are simpler because you can use a simple dish and these routers that we see DSTV using, for instance, and so on. The other thing is that the system can cope with large Doppler shifts. Now, what is a Doppler shift? I should take a minute and explain what Doppler shift is. Now, the other thing is that Sometimes because the low Earth orbit still has a bit of atmospheric effects, whatever they are, gases and stuff, some of these drag the satellite out of its orbit, and usually they have got to correct its orbit again back to what it's supposed to be. So there are navigation systems that are used to correct the position of these satellites over time. Examples, we saw those: Iridium, Global Star, Teledesic, Skybridge, Obcom, and the common one, which we all know, called Starlink. This is a new one by a company, SpaceX, which is owned by Elon Musk. Now, the low Earth orbit satellites tend to use frequencies below 1 gigahertz, but they can also use higher frequencies, have small bandwidth, and small data rates. All these maybe I should do, I will probably edit this. Or most of these, all these have been overtaken by time. Okay, I got this from the book, but really, we know, for instance, that for this one, you can see that generally low Earth orbit satellites were low rates, because 10 kilobits per second is really low. Even if you look at big low Earth orbit satellites, you're looking at up to a few megabits per second. But for instance, for Starlink, and Starlink is clearly big low Earth orbit, it can give up to 300 megabits per second. That is not a few megabits per second. So some of these points, especially the characteristics, should be put within the context of the time that our reference book was written. By the way, Ella, you remind me to share the reference book if I don't after the lecture. But some of them are no longer true, clearly. They are generally used for positioning services and for voice, and now, as we know, internet data as well. Starlink is using that for internet, as we know. I'm going to speak a bit more about Starlink. So let me use this opportunity to describe what a Doppler shift is. So if I have my base station here, and this is a user, this user is not moving. If the base station sends a signal, you know that a signal has frequency. And obviously, you guys are computer engineers, so I don't know if you know what frequency is, but I don't really want to go into it because that's a whole other topic. But the signal usually propagates with a certain frequency. Like, for instance, we know Wi-Fi is at 2.4 gigahertz or 5.7 gigahertz, depending on which Wi-Fi you're dealing with. We know that GSM is at 900 or 1800 megahertz and so on. So that is the frequency. Now, let's assume that the base station sends a signal with a frequency FC of, say, FC, yeah, let's just say FC hertz. You know, the frequencies FC. Now, if this user is stationary, that means maybe you're seated at home and you know you and the base station are stationary. The base station is stationary anyway, but you are stationary. Then you receive this signal at a frequency of FC hertz. But for moving receivers, the received signal is at FC, the original signal, plus or minus FD, where FD is a Doppler shift. In other words, Doppler shift are two words. In other words, when you are moving at high speed and you are on phone, there is an apparent shift in your frequency. Usually it's not a big shift, but there is an apparent shift in your frequency, and that can mess up the reception. So it would be preferred not to have Doppler shifts. But then because we are dealing with mobile systems, it is, you know, we have to move. That's the whole purpose of having a mobile system, that you're able to move as you conduct your business on phone. or any other gadget. So that apparent shift, there is a formula for that, but that apparent shift is what we call a Doppler shift. Now, in the satellite situation, actually, what happens is that the satellite is up here, and then I send a signal to it, and then it is on the downlink where I have my Earth station. Actually, in this configuration, it is the receiver down on the ground that is moving. In this configuration, it is the transmitter, the satellite, that is moving. Either way, that apparent shift comes from relative velocity between the two. So even if whichever one is moving, if the other one is not moving, it doesn't matter. If both of them are moving, then also you still get Doppler shift. There's a whole formula for this that has inputs like velocities and frequencies and so on. Now, why did I say FC plus or minus FD? If my base station is here and I have a user on this rod, when the user is moving in this direction, this is FC plus FD. At this point, FD is equal to 0, actually, in that perpendicular line. The moment you continue to move in that direction, now you have FC minus FD. So it depends on the relative velocity, but also on the relative position between the two nodes. Is that quite clear? I'm probably going to just wanted to give you an idea of what Doppler shift. It is that apparent shift in the received signal that emanates from the relative velocity and positioning of the two nodes that are communicating. So in the case where the satellite is the one moving, much as it's the transmitter, there is still a Doppler shift in the frequency. I hope that's clear. If anyone has a question, please put your hand up, and if I don't see it, unmute and you ask your question. So now let us look at this. Musa, please ask.
Yes, Doctor, so the positive Doppler shift, is it a good thing, or is it something that is totally unwanted in the case of the satellites?
Yeah, whether positive or negative, we would prefer not to have Doppler shift. Of course, Doppler shifts don't only happen with satellites, they also happen with any system where there is mobility. The higher the speed at which you're moving, the higher the Doppler shift, obviously. So maybe I'll come up with an equation later for you to look at. But the higher the velocity, the higher the Doppler shift. We would not want to have a Doppler shift at all, but we know that this happens in mobile systems. So if you're walking, that's okay. Your receiver can quickly track the shifting in your frequency and still receive. But if you're in a high-speed car and you're moving at a high speed, the Doppler shifts become quite big and can bring problems. Let me give you an example of how we do these things. Now, usually when we have, we know that the frequency channel is divided into what we call, actually the frequency band is divided into what we call channels, and different channels are allocated to different users. So that you, Musa, you use that, and maybe Ella uses that one. And I know some of you, I know Derek uses that one, Philip uses that one, and the others. Now, this is your frequency. Usually the center point of this frequency is at FC. And so your signal usually is like this. And this is when we say signal FC, that's what we mean. I told you that, for instance, voice is made like this. If it was just one pure frequency signal at whatever hertz, it would be, we would call that a pure tone, and it wouldn't contain any information. It would be like a beep. But when you have this signal that has a bit of a bandwidth, which we call bandwidth, in fact, then in there you have different tones and you can create some intelligible sound or voice. So now the problem is that this is at the transmitter side. The problem is that at the receiver side, the channels are the same, okay? And so the receiver expects, for instance, Philip's voice to be there. But unfortunately, it has shifted to there. So if I draw a big channel here and it's supposed to be there, but unfortunately there has been a shift to there. Or if the shift was negative, then it has shifted to there, meaning that I expect it around here, but actually it has shifted to that point. Now the receiver can correct this if it knows, if it keeps tracking that, and so it can shift quickly. But the other issue is that usually in this next channel, there is another user, so you can create these interferences, which we call adjacent channel interferences. You can, or not co-channel, adjacent channel interference. So every time you shift there is a shift in your frequency, it shifts away from where the receiver expects it, and it can cause reception issues. Luckily, if you're going to create a communication system that is mobile, you have got to think through these things and create mitigation measures so that whatever you deploy out there is able to handle. The only drawback, obviously, is that for you to give it that capability, it becomes a more expensive operation. I hope that is very clear. That was a very good question. So.
Yes, thank you.
Okay. Okay. Now, Starlink. This is Elon Musk. So if you are, in this area, you should know about Elon Musk. He's a big time businessman. I don't know if he's an inventor. He's just a businessman. He likes to create companies, to do things. You should read about him. He has a number of companies. Obviously, he has Tesla, which I think everyone here knows, the electric cars. He has this SpaceX, which is the one that he also working on taking people to Mars. He's now taking people to the International Space Station for NASA. And he also has Starlink. And with Starlink, he wants to put so many satellites in low Earth orbit so that at all times above you, there is a satellite that you can connect to and get your internet. That means you would no longer need MTN and their poor service, or Airtel and their poor service. And this is already reality. They are already serving people in the US, in Germany, UK, Sweden, and most of that Scandinavia region. It's not yet in Africa, I don't think, but at the rate at which they are moving, we should have this service at some point in the near future. So for me, that's why I was saying that low Earth orbit is something that actually, for me, can revolutionize most of what the world in a way that impacts everyone. Because the orbit is so close to us, and so even the gadgets would be cheaper. You can imagine if the gadgets are going to cost tens of thousands of dollars, no one is going to be interested in that. So they have already launched about 1,000 satellites. They need about 10,000 plus to cover the whole Earth. So they are maybe 10% away from realizing that dream. Speeds are already up to 300 megabits per second. That is quite amazing. I don't think MTN gives you that. And I know that right now, like in the US, people pay $99 a month for unlimited service through satellite. That is okay. That's about 350,000 a month, which people are already paying to people like Rock Telecom and Zuku and so on. And I be seeing them complaining all the time. If you buy about 100 GB from MTN to use per month, you'll probably also spend about that, maybe more. But there's installation, so you pay some cost. It's like how they install your DSTV. And in fact, the equipment is right here, you can see. You can see the equipment here. So you have a dish and you have a router. Okay, and I think this is the installation kits. You have a cable and so on. Yeah, typically how you do DSTV. It is now serving in some countries, and it uses orbits around 550 kilometers. The only issue with low Earth orbit is that you need many satellites, okay? but the advantage is, and it has limited coverage per satellite. That's why you need many satellites. But the advantages include the localization of the service, so that if you want to serve only in East Africa, you can do that. So there's that ability to localize the service. Being low means there is limited delay. Okay. It also means that it's easier to launch. It's supposed to be cheaper. And finally, the devices, the reception devices on Earth, like what you would call in quotes your Earth station, is considerably smaller and cheaper than if you are using like geo orbit, because there you need a huge dish to collect as much signal since it's weak, so that you can add up and get something. Okay. You can read a bit about that link. I thought there was some interesting information. It's a newspaper link, but it's quite interesting. So I put this photo here because somebody was asking about where the satellites go when they go out of service. And I remember saying there was a lot of debris already and man-made debris in space. And you can see what NASA shows us. If that is the Earth, you can see the density and yeah, the density of debris, man-made debris in the vicinity of the Earth and going into space. You can see that really around the Earth, all those white points around the Earth, those are the things like satellites that we've been talking about. There are quite many, but as you go out into space, most of these just lose their orbits and just fly into space, and so they are dotted all over space around Earth. It is possible that if you look closely, you might see like a line developing around there. I don't want to claim, but I wonder if that is the geostationary line. It is possible, because if you look at this distance, it is probably about that. So that line is I think it is geostationary. I'll put my neck on the chopping board and say that that is the geostationary link, because you can see the orbit. There's a bit more debris, a bit more debris dotted around that. But as it loses its orbit because of one reason or another, or they power it off and it's no longer under control, it flies off the orbit and can go into space. Usually they don't come back to Earth, but even if they go back to Earth, I've not had cases, unless they do a managed harvesting of that debris and bring it into the Earth's atmosphere and maybe throw it in the ocean or something. But I'm just thinking out loud. I don't think this is anywhere. Yes, exactly. So let us have actually today I have an issue with, I don't know, I have a sore throat, so I cannot teach the whole lecture, but I wonder if I should give you, just take 2-3 minutes. Let me get a cup of water and we continue and do another 10 to 15 minutes. Thank you. In a minute. Okay, I'm back. So we are going to continue. Austin. Okay, now if you look at this one, this is actually low Earth orbit. Okay, low Earth orbit. I don't know why I didn't move the photo the other side, but that is the low Earth orbit, and this is the medium Earth orbit. So you can see that here the orbit is much closer, arranged closer to the Earth. Here they are a bit, there's a little bit of a bigger gap between the Earth and the orbit. That's medium Earth orbit. Now, what we can for sure confirm based on this is that this one is a polar orbit, whereas this is, I always forget this word, inclined. This is in the inclined orbit. So for the medium Earth orbit, they are neither polar nor equatorial. They are inclined. We've already gone through these. Their altitudes range between 8,000 and 20,000, maybe, even up to 24,000. In fact, anything above low Earth orbit is a medium Earth orbit until you reach the geostationary orbit. So even if you saw 30,000 kilometers, that would still be medium Earth orbit. The geostationary orbit has got to be precise at 35,863 kilometers, give or take. Orbital period is about 5 to 10. That means that depending on the height, because you can see the height, the difference between the range is quite big. So if I see my medium Earth orbit coming over the horizon there in Namirembe, and it goes over my head, and I see it going over on the other side of town, that for me might be 5 hours if it is quite low near the Earth, or up to 10 hours if it is much higher than that. The diameter of coverage is 10,000, 15,000 kilometers. Before, we saw that for low Earth orbit, this was 8,000 kilometers. So we get more coverage because we've gone higher in altitude. The delay is about 50 milliseconds. Okay, that's still quite small compared to medium Earth orbit, which is actually geostationary orbit. The delay is about a quarter of a second, which is really big. Visible time. Yeah, actually, this is orbital period. This is the visible time that I explained earlier. The orbital period is the movement around the Earth. It does that between 5 to 10 hours. Whereas the maximum satellite visible time is 2 to 8 hours, depending on how high the satellite is. That is the thing I explained earlier. Sorry about that. Now, when you want to cover, most of the communication satellites that cover the North Pole and the South Pole tend to be medium Earth orbit satellites. But even low Earth orbit satellite contains communication satellites, and these clearly also cover the North Pole and the South Pole, or the polar regions. These are like the one we see in the other picture. Yeah. The other thing I wanted to explain, yes, so examples include GPS. The GPS is launched at 20,200 kilometers. We know that it is a navigation and position or location satellite system. Just tells you where you are. Or it can help you create a trajectory to reach somewhere, as we know how that works. I guess they also use it, I don't know, for drones. GLONASS is a similar system, but for Russia. It was launched long ago, and it has very good accuracy, similar to what you would say GPS has. But it is a Russian system, just like a duplicate, not a duplicate, but something that does exactly the same thing. And Galileo, that one is launched at 19,100 kilometers. Galileo is a satellite system that is launched by the European Space Agency, for Europe, for European nations, so that they don't have to depend on USA's GPS system. And that one is launched at 23,222 kilometers. And as you can see, that is also geostationary satellite. So much as we said up to 20, we need to remember that these are just some numbers, they are not in black and white. The other thing is the Telstar, which is also medium Earth orbit. It was the first satellite launched in 1962. It's used for communication. There's somebody who needs to mute because you're giving us background. I think I've muted you. It was first launched in the 60s, early 60s, for TV, phone voice, and telegram images. So it was able to send these across vast distances on the Earth. Then you have others like Odyssey and Inmarsat, which I talked about here. And then we know all about the geostationary orbit. Do you have any questions so far? If you have no questions, we can continue. These are the frequency bands. You don't have to cram these ones, really, but it's important to understand where a satellite works. So we have the L band, which is low band at around 1 to 2 gigahertz. We have this S band, which is 2 to 4 gigahertz. We have the C band, which is 4 to 8 gigahertz. The X band is 8 to 12.5, Q band is 12.5 to 18, K and K. K is the highest satellite band at really high frequency. And these are usually used for specific purposes. So like this one is used for the mobile satellite service. This one can be used for deep space research, mobile satellite service, and NASA, fixed satellite service, and so on. But if you look at this, it doesn't mean that from 1 to 2 gigahertz, we only have satellite frequencies, that no other service works in there, no. Because we know that there are so many things that work at 1 to 2 gigahertz, or even between 2 and 4, including Wi-Fi and 3G works in there, 4G works in there, and so on. But usually there are bits of bands that might be given to satellites. However, you'll find that most of the time, satellites tend to use the C band, these bands, from C to K. These are the higher bands which are less congested, and satellites can easily use them because there's availability of bands in those ranges. Do you have any questions? Okay, let me see. It's all right. Any questions? Because let me see what comes next. This one really needs some time, so I am going to jump over that. Yeah, let me look at this one, although this is also part of the, let me try and teach this in 5 minutes. We can come back to it if we don't finish it satisfactorily. But I think with these sorts of calculations, this is probably the first time that you're looking at this. So basically, if we go through these points, you'll notice that we have, when we are looking at the satellite link, this is the link between the satellite and the Earth station. This is the link. We want to see how it behaves. By how it behaves, we want to know the power it loses. We want to know what other effects happen along the path. And so that if I send out my signal from the satellite, for instance, I want to know how much signal will actually reach the Earth station, or the other way around, the vice versa. So for downlink, the terrestrial distance between the Earth station antenna and aim point of the satellite. In other words, if the satellite footprint is, if I have my satellite here, sorry, this is the Earth, and I have my satellite here, it will not cover the whole thing. It might cover something like that. So right below that, depending on where the antenna is facing, right below that is your maximum received power. And then as you go off, power reduces, the power you receive. But at some point, it reduces enough to say that actually beyond this, we cannot receive. So this is where the satellite coverage stops. It works exactly the same way like these signals of mobile or even FM radio. At some point, you lose a Sanyo FM. It's because there is no longer its signal there. There's things like atmospheric attenuation. So along the path, there is attenuation. That attenuation can be caused by things in the atmosphere. Oxygen is a big culprit. Water particles. So if you have rain or you have water droplets in the air, those are going to cause absorption of the signal. Then you have angle of elevation. We've already talked about this. And also, because angle elevation affects the signal in terms of the noise from the earth and also barriers on the surface of the earth and so on. And then you have also at high frequencies, these effects increase. So at high frequencies, more power is, the signal is affected in a bigger way by water, by oxygen and so on. And all these are like wireless principles, but I'm teaching wireless technologies. So we might have reach a point where I teach you some fundamentals of wireless communications, but I want to focus more on the technologies themselves. So basically we have, and I'm probably going to teach this next time again, but let me use the opportunity to take you through this. This is when I'm transmitting from the satellite to the Earth station, we call that free space propagation. Free space. The reason why we call it free space is because there are no barriers along the path. Presumably, obviously, we've seen there are things like oxygen and water and so on, and all these kind of barriers. But when we speak in this sense, we mean, are there trees? Are there houses? And no, especially if you choose your angle of elevation carefully. So we have free space propagation, and there are first principles of doing this, but actually we have a situation where we can say that power received over a certain distance is the same as power transmitted over that distance times 4 pi over d lambda. 4 pi lambda over d squared. I think that's the one. Yes. 4 pi lambda over d squared. Now, what is lambda? Lambda is the wavelength.
Thanks for coming.
Oops, I don't want to know who is speaking in our meeting, but don't do that. So lambda is the wavelength of the frequency. Because the frequency has a wavelength, it's like, you know, the repetition, the periodical signal. So lambda is usually referred to as C over F. This is measured in distance. This is C is the speed, meters per second, and frequency is in hertz. Okay. So C is the speed of light. We know that. F is the frequency. But actually in this equation, they've left lambda in there. So we can continue with that. Now, we know that loss, because actually what they are doing here is they are doing loss. LDB is the loss in dB. I don't know where it is in here. So you can see PT is the power transmitted, PR is the received power, lambda is the carrier wavelength, and D is the propagation distance. So loss is equal to, how do I know how much power I've lost? I will get the power I've transmitted minus the power I've received. If I transmit 20 watts and I receive 10 watts, I've lost 10 watts. As simple as that. Now, this one that we are doing is called large scale loss. It is the loss you suffer over a long distance. There are also other losses you suffer over short distances, but these are more in fundamentals, and maybe we'll study about them. So let me get this equation I use in dB. dB is log. If you don't know what dB is, you let me know next time I go through it. But actually, I think you should already know what dB is. It's very easy to convert things into dB, dBm, and dB watts and watts and so on. So we usually use log. So let's say 10 log 10 of PR. If I convert this whole thing into dB, becomes 10 log 10 of PT plus 10 log 10 of 4 pi d over lambda square. Right. I hope it works out. So anyway, now this 10 log 10 of a value gives you its dB value. So I can say PR dB in dB. And clearly this one is also PR in dB, okay, this part. And so then I can say that, and we know that in logarithm now this power will come and multiply there. So then we can say that we have PT in dB minus PR in dB is equal to, so this one goes the other side because I've moved this one here and I'll move this term the other side, which gives me negative 20. This 2 comes down here to multiply, negative 20 log 10 of 4 pi d over lambda, okay? But now this is my loss. But actually, if I remove the negative, I can make it 20 log 10 of lambda over 4 pi d. Okay, and I think this is similar to, yeah, this is similar to what they have here. No. Negative 20 log. So anyway, let me go through. So you have PR is equal to PT plus 10 log 10, blah, blah. So then you have PT minus PR is equal to that, which is negative 20 log 10, yeah. So then my loss is equal to, it's quite confusing. Mwesezi, why do you guys keep going out? This is quite confusing actually, but I think we'll go through this again next time. If we just open a new slide just to do it again so that we don't leave that one hanging, because I'm wondering why yeah, I don't quite agree with them, but I need to look at it. So anyway, so you have PR is equal to PT lambda over 4 pi d squared. I believe we got that correctly the first time. Okay, so we had our, I think we had this wrong in the first place. It is supposed to be lambda over 4 pi d squared. Sorry about that. Lambda over 4 pi d squared. Yes, that's really the one. Now we did our logarithm. We got PR in dB is equal to PT in dB plus 10 log 10 over lambda over 4 pi d squared. That will come here, so that PR in dB is equal to PT or PT in dB minus PR in dB is equal to, this one goes there, negative 20 log 10 over lambda over 4 pi d. Okay. So then this is loss. It is PT minus PR. So you can say loss is equal to negative 20 log 10 of lambda. Okay, that one directly. Minus, now because these ones are down, they will come up as a minus as well. So in fact, it becomes a positive, which is 20 log 10 over 4 pi d. Okay. Now, if you separate the 4 pi from the d, you're going to have 20 log 10 of d plus 20 log 10 of 4 pi. And 20 log 10 of 4 pi is what they have as 21.98 dB. So with this equation, all I need is to know the distance between the satellite and the Earth station and the frequency so that I can calculate the wavelength using this equation. And then I will know the loss that I'm suffering. So for instance, in this quiz question, I had what is the loss suffered by a geosatellite link. And I know that already distance is 35863 kilometers. The only thing that I don't know is the frequency. Okay, so ideally I should be giving a frequency. I could give you like maybe for instance, I could say at 5 gigahertz, for instance, and then you can find the wavelength and do the math. Actually, wait a minute. That's Musa. Yeah, actually what they've done here for them is that they've said that PR is equal to PT lambda, this is not plus, lambda over 4 pi d squared. They know that the fraction PT over PR is equal to 4 pi d over lambda squared. Okay, and then they know that if I take 10 log 10 of the fraction PT over PR, if you take logarithm of a fraction, it becomes a minus, is equal to 10 log 10 of 4 pi d of lambda with a square. Okay, so then this actually becomes 10 log 10 of PT minus 10 log 10 of PR, which is what we had as PT dB. This one I use square brackets minus PR of dB. And then this 2 becomes here, so you still have loss equal to 20 log 10, in this case 4 pi d over lambda. Okay, so in fact that's where we were confused, or I was confused. I don't think you guys were confused. So then this becomes 20 log 10 of 4 pi plus 20 log 10 of d minus, because lambda is down, so it becomes minus 20 log 10 of lambda, and you get the same thing. So we'll continue from here next time, and we could even actually start with a little bit of a recap. But today I want to stop here. I didn't expect to teach an hour and a half, but thank God. Have a nice evening, and I think our lectures are on Friday, so I think we'll meet again on Friday. I'll try and set up Muele for you. And so if I do that, I'll share the link or the code with Ella, and you can join the class. This is, yes, Keith. This was large scale loss. Large scale loss is the loss you suffer over large distances. Large distances can even be 2 meters, so that can be large scale loss. Things that cover a short distance also suffer large scale loss. Small scale loss happens at a fraction of the wavelength. So if my wavelength is 1 meter, loss that is happening within that can be described as small scale loss. And that one is more of the fluctuations in the power. Like for instance, when people get the person on the other side starts breaking, you move a little and usually things stabilize if it like so small distances can cause significant changes in power. Okay. Have a nice evening and see you soon.